In this video, I'm going to walk you through the post-lab for Lab 6, the boiling point elevation and freezing point depression. This post-lab assignment has two data tables. Some of the spots on this data table are things that you wrote down while you were doing the lab. So for example, you recorded the boiling point of pure water. You recorded the volume of water that you used. I think it's 100 milliliters. You also recorded the mass of NaCl. That's about 4 grams. You recorded the boiling point of the sodium chloride solution. I think that's everything that you recorded while you were doing the experiment. So we'll just make a note that this is data that you obtained while you were doing the lab. Now, the first thing that we're going to calculate is the mass of the water. The problem tells us that we're going to assume the density of the water is 0.998 grams per milliliter, and we're going to use this to calculate the mass of the water from its volume. Density, as you know, is mass divided by volume. So if we're trying to calculate the mass, we want to rearrange that density equation so that it is mass equals density times volume. Your density is right here, your volume is right here. This will give you the mass in units of grams. The mass of NaCl, this was a number that you wrote down in the lab, roughly 4 grams. And the next thing that you're going to do is calculate the moles of NaCl. You're going to do this using the molecular weight of NaCl, which is about 58 grams per mole, I think. I don't really have this memorized, so you really should double check and look it up and make sure it's right. And so what we're going to do is do a straightforward gram to mole conversion using the molecular weight of NaCl and using the mass of NaCl that you reported in the lab. Then the next thing we have here is the boiling point of the NaCl solution. Again, this is a number that you took from the lab. Now here's where things get a little bit tricky. The next thing is asking us to report the change in temperature of the water, or at least that's kind of what it looks like. We see that delta symbol, delta T. We know that typically when we look at the symbol delta T, that is referring to the final temperature minus the initial temperature. But notice that this is not just a delta T, this is a delta TB, not the same as delta T. So even though this is accurate, this is not what the problem is asking us to do at this point. This wants us to report the change in boiling point for the water when it's water all by itself versus water in this solution. So we want to do the boiling point. I'm just going to write the, what's the easy way to write this? The boiling point of NaCl solution. I'm going to abbreviate that SOLN, minus the boiling point of the pure water. So we want the difference in the boiling point between the two, because we're looking at how the sodium chloride has affected the boiling point. And this should be an absolute value. This should be a positive number. So just make it a positive number. Put these two in the right order so that it's a positive number. The Kb for water, that's a constant. That's something that you can look up. It's pretty easy to find if you don't happen to just have it memorized at this particular time. You can Google it. Kb of water is 0.5. That's kind of funny looking notation. 0.512. That O there is supposed to be a degree symbol. 0.512 degrees C per molality. So that's a constant. 0.512 degrees C per molality. Again, this is a constant. Now we want to calculate the molality, not the molarity, the molality of the solution, and that is going to be the moles of sodium chloride divided by the kilograms of water. Molality is a weird solution unit. It is the moles of our solute divided by the mass of our solvent in units of kilograms. We've got our moles of NaCl right here. And then as far as kilograms of water, we've got our water in units of grams up here. We just need to convert it into kilograms for it to work down there. Now the last thing that we're going to do is calculate the experimentally determined Van 't Hoff factor for sodium chloride. And to do that, we're going to be using the equation delta TB, the change in the boiling point, is equal to I, which is the Van 't Hoff factor, times Kb times molality. And again, we're trying to solve for I, which means we want to rearrange this equation, and it's going to look like the change in boiling point divided by the boiling point constant times the molality. Our change in boiling point is right here. Our Kb constant is right there, and our molality we calculated right here. The actual value, or the predicted value of the Van Hoff factor for sodium chloride is 2. There is a little bit of deviation from that predicted value, but you should expect to see a value of I that is, maybe somewhere between 1.5 and 2.5. Now for our next data table, we're going to do basically the same thing, only this time we're doing this with freezing point data. So first you recorded the freezing point of your water, the volume of your water. You're going to use that to calculate the mass. You're going to use the volume to calculate the mass, just like you did on the question number 1. You're going to record the mass of your ice, and then you're going to calculate the total mass of water. This is going to come from the mass of the liquid water plus the mass of the ice. This is something that students get wrong pretty often. They just report the mass of the liquid water, but solid water, that's water also. So you want to take this mass and this mass here and put them together. Now you have your mass of NaCl. You're going to convert that into moles, just like we did on question number 1. And you're also going to report the freezing point of your sodium chloride solution. Now down here you have another delta TF, another change to the freezing point. So this is going to be like the freezing point of pure water minus the freezing point of the solution. Make sure that it is a positive number, so we want it to be an absolute value. And then we want our Kf for water. So I've got this thing, I left it open so that we can look up the Kf for water. The Kf for water is 1.86. I don't know why. It just says 1.86 degrees. 1.86 degrees Celsius per molality. This is reporting it in some funny looking units there. It says 1.86 times kilograms divided by moles. Remember that molality is moles per kilogram, and so what this person has done is inverted the kilograms and the moles in this part and kind of just made the units look really unconventional. We'll just kind of make that go away. So almost done. We're going to calculate the molality of the solution, which is going to be your moles of sodium chloride divided by your kilograms of water. And you want to make sure that you want the kilograms of all of the water, not just the liquid water, but all of it, the liquid and the solid as well. And then last but not least, we're going to calculate the experimentally determined value of I, just like you did on the question number 1. So again, our predicted value is going to be about 2, and you won't expect to see a number that is perfectly 2, but somewhere in the ballpark of 2. Like if you get 50, that means you probably did something really wrong, and try again.